Good day to one and all. This is a module of group theory for chemists, and in this lecture we will see about symmetry elements. First of all, what is symmetry? Symmetry is an integral part of this universe and its creations. You can see symmetry in flowers and in every object the nature has created. As such, I think you would have conceived what is symmetry. It is a sense of regularity which you can feel when you see an object, right from a beehive to a rangoli, which we do it in everyday routine life. And now, how is this symmetry related with chemistry? Chemical molecules are very much symmetric most often, and the crystals crystallize themselves following a particular symmetry, and these are the class of compounds which are known for their symmetry. And of course, there are also the compounds in chemistry that do not have symmetry, like the case of proteins, but with respect to this group theory, we are very much related to symmetry concept in chemistry. Now let us reflect for a moment and try to clarify the concept of symmetry in our mind. The symmetric is some regularity which we see, and the asymmetry is a irregularity. Now on this basis, let us try to categorize these molecules as symmetric or not. This carbon tetrachloride is symmetric, and this Taj Mahal picture is also symmetric because you can cut this into two equal halves, and this tiger is very symmetric, and this starfish is also symmetric. This drop of water is not symmetric. I hope the concept of symmetry would have engraved in your mind with clarity. Now, what makes an object symmetric? It is a symmetry element which makes an object symmetric. The symmetry element is nothing but it's a plane, a line or a point about which the operations like reflection, rotation or inversion is performed in a molecule that results in an indistinguishable appearance more than once. These operations like rotation, reflection and inversion performed on symmetry elements are termed as symmetry operations. Now let us see what are the symmetry operations that are available. Identity operation, and it is associated with doing nothing, and the symbol is E. The axis of rotation, it is the rotation of a molecule about an axis Cn, where n is given as 360 divided by the degree theta. Theta is the angle through which the object is rotated to get an indistinguishable appearance. And this angle, this axis is called a Cn axis. Then we have plane of symmetry, whose symmetry operation is reflection, and it is represented by sigma. Improper axis of symmetry, it is a rotation along the Cn axis followed by reflection in the plane perpendicular to it, and is depicted by Sn. One more symmetry element is missing in this table. It is nothing but center of inversion, and the symmetry operation is inversion, and it is represented by I. Now we will see these symmetry operations one after the other. The axis of rotation or rotational axis of symmetry. It is the axis through which, when the molecule is rotated, an indistinguishable appearance is obtained more than once. For example, consider the case of water, in which you can imagine an axis at this point through which, when the molecule is rotated, an identical appearance or the indistinguishable appearance is obtained. As the angle is 180 degree, angle of rotation is 180 degree, the axis is called as C2 axis of symmetry. It is more clear through this image. Now, this particular molecule is having C3 axis of symmetry because it rotates through an angle 120 degree to obtain the indistinguishable appearance. Similar is the case of this molecule, which also exhibits C3 axis of rotation. I hope we are clear with this axis of rotation. Now let us pause for a while and test our understanding, and let us try to identify the axis of rotation in these molecules. When you see the case of this first molecule, you can see that an axis at this point is the axis of symmetry, and it is called a C3 axis of symmetry because you get an indistinguishable appearance after the rotation of 120 degree. So 360 divided by 120 is going to be 3. So this axis is C3 axis of symmetry. Next, in this molecule benzene, this axis at the center is the axis of symmetry, and it can be designated as C6 because you get this axis, the rotation about 60 degree gives an indistinguishable appearance, and so this axis is called as C6 axis of symmetry. And for this molecule, you can see that this is an octahedral molecule in which this axis is C4 axis of symmetry because you can see that the molecule appears as the same by rotation about 90 degree along this axis. I hope we are clear with this axis, and apart from this particular axis, we can see other axes in molecules. So, in the case of multiple axes, the axis of highest order is the principal axis, and it is generally assumed in the z-axis away from the plane of the board or the computer. In the case of benzene, which we have seen earlier, we have identified a C6 axis of symmetry, and apart from this C6, we can see other axes like C2 axis 1, 2, 3 and another 6 C2 axis of symmetry. So these C2 axis of symmetry are called as secondary axis. Similarly, in this molecule of BF3, you have a C3 axis and you have another 3 C2 axis that is lying in the same molecule, and C3 axis is the principal axis and C2 axis are secondary axis. I hope all of us are familiar with the primary and secondary axis of rotation, and we can just verify our understanding by solving the primary and secondary axis of these molecules. The ethylene has a C2 axis at this point and is the primary axis. Apart from that, there are 2 other C2 axes lying here. So these are the secondary axes which are termed as C2 prime. And in this molecule, there is only one axis of symmetry, that is C2, that is extending in the perpendicular direction of this computer, and this is the only axis of rotation. There are no other secondary axis of rotation. And in this molecule, there is again only one axis of rotation, that is C2. And now, let us go to the second symmetry operation, that is plane of symmetry. It is a plane of symmetry is any plane that cuts the molecule into 2 equal halves such that one is the exact mirror image of the other. To understand this better, this picture will be of help. and you can imagine a mirror here, and the molecule is the exact reflection of the other. And now there are three types of planes of symmetry: horizontal plane of symmetry, vertical plane of symmetry, and dihedral planes of symmetry. We will see each of them one by one. Horizontal plane of symmetry. Symmetry plane that is perpendicular to the symmetry axis is called the horizontal plane of symmetry. See, for example, the molecule has a C3 axis perpendicular to this, and if any plane that cuts the molecule perpendicular to this principal axis is called as the horizontal plane of symmetry, and it is designated as sigma h. In the case of water, you can see that this is the C2 axis of symmetry, and you don't have any plane that is perpendicular to this axis. So this particular molecule does not have a sigma h. And in this case, HCF4 molecule, again you can spot a C4 axis in this direction, and you can see a plane that is perpendicular to this axis, and that is called as sigma h. Now, the vertical plane of symmetry. It is a plane that goes along with the axis of symmetry and cuts the molecule into two equal halves. Now, horizontal plane also cut the molecules into two equal halves, but it is perpendicular to the principal axis, while the vertical plane also cuts the molecules into two equal halves, but is along the principal axis. So here in the case of water, this is your C2 axis, and there are two planes, this plane and this plane, molecular plane. Both the planes are going along with the C2 axis, and so the two planes available with water are both vertical planes. Hope this point makes you clear about the vertical planes. Now, some of the vertical planes are such that they cut the molecule into two equal halves, and they bisect the angle made by two consecutive C2 axes. Such a plane is called a dihedral plane. In other words, it's the vertical plane that bisects any two consecutive C2 axes is called a dihedral plane. And in this case, in this molecule, let us imagine it is HCF4 or PtCl4 minus. And in this molecule, you can see that there are two C2 axes, and there is a plane that cuts the molecule, that cuts the two C2 axis through the center, that bisects the C2 axis through the center, and such a plane is called a dihedral plane. And similarly, there are dihedral planes in benzene, three dihedral planes which cut the edges of the benzene ring. Now let us pause for a while and try to identify the vertical, horizontal and dihedral planes of symmetry, if any. And in the case of first ethylene, we can see that there are two vertical planes, because this is your axis of rotation, and these two vertical planes that are actually running along with your axis of rotation, and there is one horizontal plane that is perpendicular to your axis of rotation. Now in the case of your next trans dichloroethylene, you can see that this is your C2 axis, and you have a plane that is perpendicular to this C2 axis. So this is the horizontal plane. And now you have the cis, and you have two vertical planes. This is your C2 axis, and one vertical plane goes along the C2 axis, and another molecular plane that also goes along the C2 axis. So the two planes in cis dichloroethylene are vertical planes. Now we will go to the improper axis of rotation.